On the real plane, which is what we've been used to for plotting points or graphs, we have an x and a y axis. So for example, if we were plotting this point, we would go 2 to the left and then 3 up, and this would be the point on this real axis. However, when we're graphing on the complex plane, the x-axis is the only one that's real, and then the y-axis represents the imaginary. So this looks a little different. If we have, for example, a negative 2 plus 3i, this is saying that we're going to go ahead and graph this as our real component, and this is going to be our imaginary component. So we will go 2 to the left, and then we go 3 up on this imaginary, and it will be right here. And depending on what you're looking at, some places put a dot, some do a line segment from the origin to the dot, because it's convenient to go ahead and represent this as a vector for many reasons, including for science and further mathematical studies. I'm going to go ahead and draw it as a vector. So going from the origin to the point as shown by the real component and the imaginary component that have been graphed. So for problem 2, let's go ahead and graph all 5 of these points, A through E, on the same complex plane. I've labeled my x-axis as the real axis. That's what the RE stands for. And my y-axis is now called the imaginary axis. So for point A, we're going to go 2 to the right and then 4 down. For our complex number B, that's 4i, I'm going to go 1, 2, 3, 4 up on the imaginary axis. Point C is a negative 4i, so I'm going to go down. For point D, if it helps, we could write this out as negative 1 plus 1i. So that you're aware that the real part, there is a negative 1, so I go down 1 down. But then the negative 1 means I go left 1 on the real. That's the real. This is the real. And then the imaginary part is going to be a positive 1. So I go 1 to the left and 1 up. It's pretty helpful and useful to always express the complex number in the standard form. So the standard form, for example, is a plus bi, where this is the real part, the a is the real part, and the b is the imaginary part. So for example, if we wrote point B in that standard form, it would be 0 plus 4i. And that's why when we graphed B, up here, we didn't move on the real axis. We only went up 4 on the y-axis, quote unquote the y-axis, because it's the imaginary axis. Okay. So with that being said, I mean, you would think 4 is easy to graph on the complex plane, and it is if you recognize this is 4 plus 0i. In other words, there is no imaginary part. It only has a real part. So I'm going to go ahead and graph that on the real axis. And this is my point E. The modulus is essentially the absolute value of the complex number. So it's the distance from the origin to the point. That's why previously I graphed the complex numbers on the complex plane with an arrow, or what we call a vector, for those of you taking physics. And because it's the modulus is showing that geometric distance from the origin to the point. And when we do the modulus, we are doing an absolute value, but it honestly looks like the Pythagorean theorem. Okay? And there's implications of that you'll find out more about in future math classes if you get that far. Nevertheless, notice that we are looking at the standard form of a complex number, and that we're only putting a and b into the formula. We're not putting I in the formula. There is no I in here. Furthermore, you should note that everything in here is being squared, so we're not going to get any negative answers out of this. There is no minus, there are no negatives. Everything's going to go into this thing positively, and no i's will be going in there. So if we look at problem 3, if we rewrite this as a complex number in a plus bi form, the absolute value of this is going to be negative 5 squared plus 0 squared. We're only inputting the actual real and imaginary parts. We're not typing in the imaginary unit itself. Now, of course, this ends up being a positive 25. We've been practicing with parentheses quite a bit. Plus 0 squared is square root of 25. At this point, we should use a prime factorization tree if we need one. But in case if you need one, it's 5 times 5. We pull out a pair, and the square root of 25 is simply 5. So that's A. Complex number part B. Again, we are taking the real part and the imaginary part without actually putting in the imaginary unit. We go ahead and simplify this to get 9 plus 4, which is square root of 13. This is a prime number. You could do a prime factorization, but it's going to be 1 times 13, and that's it. This cannot be broken down any further. So the answer to part B, this is the absolute value, or the modulus, right? This is the modulus of the complex number for part B. If it helps to rewrite the complex number for part C like this in this form, you can identify that this is your A and this is your B, right? The 2 is your real part and the negative 1 is your complex part. So to find the modulus, or the absolute value, we'd go ahead and put these in. Remember, there are no minuses. It's a plus. Mr. Rover, there's a negative. Yeah, it goes inside of the parentheses. It goes inside of the parentheses like we've been practicing. And this ends up being 4 plus 1 because 2 times 2 is 4. And negative 1 times negative 1 is a positive 1. This gives me a radical 5, which again happens to be a prime number, so we're not going to break this one down. Here is part D. We set this one up as a 0 squared plus a 3 squared. Once again, we're not using the I in the calculation of the modulus, or the absolute value. That's a 0 plus a 9, which is a square root of 9. And the square root of 9 ends up being just a 3. Please be mindful that if your modulus, if your square root ends up being a number that you can break down with a prime factorization tree, you should do that. And if you need a remembrance of that on how to do that, go back to the video that we did where we introduced to you complex numbers. So in this case, we're simplifying this a bit for you to show you that each of these 5 points on this complex plane is a complex number. Okay, so you don't have the numbers this time. You just kind of have to eyeball it. And Z tends to be a letter that we tend to use for complex numbers. For example, we would say that Z is equal to A plus BI. So we know that all of these Z's right here are A plus BI form complex numbers. But the question is, which one's got the greatest modulus and why? Well, if we were to start drawing arrows from the origin to each of these terminal points, the question becomes, which of these arrows that I just drew is the longest? Because we said earlier that the modulus is the distance from the origin to that complex number. So looking back at this, the question is, which one has the greatest modulus? The one that has the longest arrow. I don't think you need my help answering that question. Hint. So make sure you pick the right one. Now, the answer is why. Well, the one you picked is the complex number with the greatest modulus. Not because you calculated it, but because you look at the geometry. You saw that the one with the longest arrow, quote unquote, or the longest distance from the origin to the point on the complex plane is the one that's going to have the greatest modulus. For your summary, how different is graphing on the complex plane compared to regular plotting of points from back in the day.